Okay, before I start, I'd like just to emphasize a few things that I've already posted on the course web page. So if you go to the course web page, and if you remember this file, you know, this announcement that I have posted a few days ago, these are the most important parts that you need, or things that you need to remember. First, that we will have quiz 2 on April 9th from 9:30, so the same time as the lecture on April 9th, Thursday, April 9th. So it's going to be next Thursday, or the Thursday after, I believe, right? Today is 26th, so yes, the Thursday after. And the final exam, okay, the final exam will be Tuesday, April 28th from 9:30 to 11:30. So this is 2 hours. Quiz 2 is going to be 1 hour from 9:30 to 10:30. And also I will be available, as I mentioned before, every Monday, Wednesday, and Friday from 12 noon to 2 p.m. These are the virtual office hours. It's first come, first serve, so it's open for all the students from different courses. So please utilize this if you have any questions, anything that's not clear, and you know, just join. You know, if you go down here, you'll find the link for this Zoom ID. If you just click this link and open the Zoom, you can join this office hour. Okay. And for homeworks, we're gonna have 1 or 2 more homeworks, and as usual, like I will post them, upload them on Canvas. You print them, solve them, and scan them, and then upload them back again on the for grading. Okay, on the Canvas. That's it. Do you have any questions about any question about these points?
Yes, sir. 1 second.
Okay.
Sorry. It says final exam Tuesday, April 28th, 9:30 to 11:30, and then it says final exam on Monday, April 30th from 9:30 to 11:30.
Okay, again, this is the copy paste. Let me go here. Okay, so the final exam will be 30th, okay? So this is Thursday, okay? Thursday, 30th, okay? So let me...
The lab final is on the 28th, right?
Yeah, so, okay, this is... Okay, so let me just check here. So 28th is Tuesday, 29th is Wednesday, 30th is 29th is Wednesday, 30th is Thursday. Okay, so this is 30th Thursday. So both have errors. Okay, so let me just change this. Okay, so this is Thursday, April 30th. Okay, and this is Thursday, April 30th. Okay, so I think this is correct now, because according to this, so we have it on 30th. Okay,
sounds good, sir. Thank you.
Thank you. So I apologize again, this is the copy paste because I did this for all courses, so sometimes I modify the time and I forget to modify date or the day. Okay, so this is, I believe it's correct. So this is Thursday. So quiz 2 is on Thursday, and also final exam on Thursday, but this is April 9th and this is April 30th. Okay, and both of them will be on the same time of the lecture, but this one will be 1 hour and this one will be 2 hours. Okay, and I will send you the instructions. Most likely the quiz will be online, so you have it will be on Canvas, so you will have the question, you know, like you open the exam on time, 9:30, and then you answer it. You like some maybe multiple choice questions and some numeric questions. So you put the numbers, you answer the questions, and your work, you know, you have to work on papers, you know, like to with the formulas and equations and these things. You scan them at the end and send them to me. Okay, so don't lose, like, you don't lose too much grades or marks because the final answer was not correct. Okay. Any other questions?
Can I ask a question regarding lab, please?
Yes, go ahead.
For the lab that is due tomorrow, are there new instructions by any chance for the the DAC, the virtual DAC?
Like, didn't you solve the issue last time? I remember someone told you how to fix it, and you said that's okay.
It still doesn't give me any kind of output or anything like that.
Okay.
So that was like, I can invert the lines. That was the issue that Armando helped me fix. Maybe I'm still not understanding this. I can talk to Armando again and get back to you.
Yes, yes, please try to just implement the LabVIEW virtual instrument that we have and just submit it. Okay.
Okay.
We're
Sure.
not gonna use it anyway because you're using now Multistage to implement the circuit. And as I told you, like, I contacted Dr. Shervikar, and he said that this is the serial number that students could use. And I also checked the virtual website, you know, desktop, and it works fine. The only thing you need, maybe if after you download or you upload the files to the virtual machine, you save them as 14, you know, edition 14, because they are made in using version 13 of Multistage. So if you save them as 14, they would work fine. So once you download them, open them, okay, in the virtual machine or virtual desktop, and then click save to save them as .14 or MS14 or something like this. And I tried it and it worked fine. Okay.
Okay, sir. Sounds good.
And I fixed this, you know, reverse connection of the outputs and input ports for the SAR and for the D-latch. So I think now you should work fine. You just connect them, and you have X0 or S0 as the least significant bit, and S3 or D3 or X3 as the most significant bit. So you just make sure that you connect them accordingly. And even R's, you know, I also identified R0, R1, R2, R3. So R0 corresponds to the least significant bit, and R3 corresponds to the most significant bit. Okay. And if you still have questions, just post it on the website. Okay, if you go here, like any course, like for this course even, you will find here course discussion in this tab here, or this link here. You can post any course related questions here, okay? So that everyone can answer, or everyone can share, you know, the information, or I will answer for everyone. But if it's something personal or regarding marks or grades, just send to me personally, okay? Okay, any other questions? Okay, so let's go back to the slides. We were talking about the differential pair, differential amplifier, and multi-stage amplifiers. In the differential amplifier, quickly, I will go quickly through the slides. We introduced what is the differential amplifier, differential pair? So it's basically two identical or matched transistors with two matched loads and a tail current source and two inputs, okay? And also two outputs in general, okay? If you would like to use them, you can, or if you'd like to use just a single output, like the regular operation amplifier, the 741, we just use one output, okay? So just we omit one of them and we use the other one. But you still have the option of using the two inputs, okay? And we said that the major advantage of this structure or this configuration are two things. The first thing is that this configuration kills the noise, as I mentioned here. If you have two inputs, you can dramatically reduce the common mode noise, because the noise will hit the two terminals at the same time and it will be canceled at the out, while the signal is amplified, because the signal is differential signal and the noise is common mode. So these two terms are important, the differential signal and the common mode signal. Differential signal is a signal that's applied to this terminal, which is different than this one. So like if you add a voltage source or a source here between these two terminals, then it's a differential signal. But if you add a source from this terminal to the ground and the same source from this terminal to the ground, this is a common mode signal, okay? So you need to understand. So like if you go here, so this is what this is. Okay, this is the general. This is common mode because you connect the same signal to both inputs at the same time. But something like this is called differential mode signal. Okay, and this is why we call this VI differential. So it's actually basically you connect the signal between this terminal and this terminal, because this is ground, this is ground. So this means the source is connected between the two inputs, okay? So the first advantage is that this configuration will reject the common mode signal and will respond and amplifies the differential input signal, okay? Second advantage is that with this configuration that's symmetric like this, it already reduces, as I said, rejects the common mode signal. And one of the common mode signals, other than noise, is the DC signal. So the DC bias in the circuit is common because the DC current here is the same as the DC current here, which is half of this one. So the DC current will be already neglected from the output, rejected from the output, because it's the same. So we can consider the DC bias or the DC current in both legs as a common mode signal. So this transistor or this amplifier will reject this DC at the output even without a coupling capacitor. You don't need a coupling capacitor to link this to the next stage. So this is the first amplification stage, and you already isolated and rejected the DC bias. So you don't need any coupling capacitor. And the reason that we don't need, or why we don't desire like having coupling capacitors, because the capacitors, if you fabricate them inside an integrated circuits, they are gonna be like very large, you know, like they will consume a very large size in the IC, okay? And you'd like to reduce the size of the integrated circuit as much as we can. So let me give you an example. For example, if you'd like to design a very small capacitor of 10 picofarads, it's a very small capacitor. You might need at least 10 times the area of a transistor to design one capacitor of just a small value of like around 10 picofarads. So let alone, like, you remember the coupling capacitors that we used to use? They are in microfarads. So they are 1 million times higher than 10 picofarad, right? Or 1 picofarad. So imagine the size, the huge size. So you cannot insert in an integrated circuit a large capacitor in microfarads. This is impossible. So this is why we in the integrated circuits, we avoid coupling capacitors and these large capacitors. We can add like just a very small capacitor if needed in picofarads, that's fine. But you have to know that even this small capacitor will occupy a large area compared to the transistor itself, okay? So these are the two main advantages. And then we studied the two cases, the common mode input case and how the transistor or the differential pair operates. And we said that the final thing is that the output will be 0 Why? Because the VD1, the output 1 and output 2 are exactly the same. If you apply the two signals the same and the two transistors and the two legs are identical, then this voltage at the output will be the same as this voltage at the output. So if you take the differential output, and you have to remember that we have differential input and differential output. So when I say differential input, I mean V input 2 minus V input 1. When I say, V input 1 minus V input 2. When I say the differential output, I mean V D out or V out 1, V output 2 minus V output 1, or VD2 minus VD1. Okay, so these are two things. If you'd like to have a single-ended output, you just take it from this side or this side. That's it. Okay, so for the differential, for the common mode input, the differential output is 0. Okay, of course, the single-ended output is not 0. If you take the signal only from this side, it's not going to be 0. If you take it only from this side, it's not going to be 0. But if you take it from the difference between these two outputs, because they are exactly the same in common mode operation, then the output will be 0. So the differential output for the common mode input is 0. The single-ended output for the common mode input is not 0. Okay, so, and we also identified the maximum and minimum, the common mode range, which determines the maximum and minimum input, common mode input for this operation mode. And we said that the VCM max is this value here, and the VCM min is this value. Okay, and we studied example 9.1. Then we move to the second operation mode, which is the differential mode. Okay, and we said in differential mode, this voltage is different than this one. And we studied the extreme cases. If we have like the higher the voltage of VID1 compared to VID2, the higher the current here, so the lower the voltage here, and vice versa. So whenever you increase this voltage, you change the current and you change the output voltage. So now the output voltage VD1 is different than VD2, depending on the difference between these two voltages. Okay, so it's kind of balancing, thing. If you increase this one, you make this one higher than this one, or the current lower than the current. And vice versa. Okay, so we are studying now how much is the voltage you apply to input 1 that can steer all the current all the way to this side or this side. Well, we analyzed this and we figured out that it's working like this. It's a nonlinear relation between the output current and the input VID. And this curve is depicting this characteristic function or equation, or transfer characteristic, if you'll say transconductance characteristic, because this is output current versus input voltage. So it depicts I1, which is this one here, and I2, ID1 and ID2. When you steer the current, when you increase VID all the way to square root of 2 V overdrive, you steer all the current to the first transistor, because the first transistor will be working higher. So ID1 will be much higher to the limit that it will reach the same value of the current, the tail current I. So if you apply VID as the square root of V overdrive, now this current, someone has a question or? Okay.
No, people are talking about the audio.
Oh, is there a problem with the audio? Can you hear me?
Yes, 100%.
Okay. Okay, thank you. So if you have a problem, just check your speakers or anything. So if you apply a voltage with the maximum of square root of 2 V overdrive here at this input, you have this current at its highest value, which is I, right? Because we said in the equilibrium or in the common mode, this I is split evenly between this leg and this leg. But if you increase this one compared to this one, then you steer the current to this side. So this side will have more current until you reach the maximum here where the current, all this current is flowing here only and nothing is here. And this one is turned off. The same can happen to the other side. If you apply a negative voltage, or means that this voltage is higher than this one, if you put this as ground and increase this side, that makes this voltage negative, right? So if you increase this voltage on the other side, in the negative side, until you reach to negative, I think there is a negative sign here missing. So this is, oh yeah, because this is absolute value. Anyway, so this is negative square root of 2 times V over drive. Then you steer all the current to the other side to the maximum of I, while the other current would be 0. And the exact equation of these curves are these ones, okay? By the way, an approximation of this equation happens when you work in a small signal. So this is the large signal, right? So if you work in a small signal, how much do you think these equations could be simplified to? If we assume that we're working in the linear region, a small signal means the VID is around 0. It's very small. It doesn't go all that much of square root of 2 of V over drive. Let's say it's just from minus 0.2 to plus 0.2. So if you're working in this, just this area here, or this range here. So we're working in linear region, right? Because this curve is non-linear, but if you work in a small signal, it's going to be linear, right? You're working, and this is preferable, you know. So this is why when you operate the transistor, we don't operate in the high in the large signal or large inputs. We work in the AC or the amplification as small signal. So what do you think that we can simplify this to if we just assume that VID over V over drive is very small? It's just in this vicinity here, in this range, from minus 0.1 or 0.2 to 0.1 or 0.2. How we simplify this? This is ID1, the exact curve here is ID1 equals I over 2 plus I over 2 again, okay, times VID over V over drive, which is this ratio here, times the square root of 1 minus VID over 2 times divided by V over drive squared. If I tell you that VID over V over drive is very small quantity, how would you simplify this? We still need to keep ID1 as a function of VID over V over drive. Any answer?
Can it be approximately 1/4?
Sorry, can you say that again?
Can it be approximately 1/4?
1/4?
Yeah, approximately.
No, you are not going to get rid of these two because you need to keep this as a function of VID over V over drive. So don't neglect this part here. The only thing that you can neglect is this term here, right? So let me just use the marker. So this one, we could say that it is 0, right? Why? Because it has VID over V over drive squared. And if VID over V over drive is very small value, then the square of a very small value, 0.1 square means 0.01, right? So this is very negligible compared to the 1. So we can say this approximately equals 1, right? So this is the linear equation. If you neglect this part and you assume it's 1, you end up with this, okay? And this is nothing but a constant plus a constant times VI over V over drive, okay? So it's just a linear. This gives you this linear line up to here, and this linear line up to here. So if you work in a small signal, someone has a very glitchy. Okay, let me try something else, okay? Can you hear me now? Okay. So let me try. Okay. Okay, so it's from your side. Okay. So did you follow this? Like, do you agree with that? Like now, if you assume that VID over V over drive is very small. Okay, let me just delete this. Okay, so if VID, because this is simply VID over V over drive divided by 2, right? So this is half VID over V over drive. If you assume that this value, this ratio is very small, that means you are working in this area here, for example, then this is negligible compared to the 1. So the square root of 1 is 1. So you end up with this. This is a linear, right? This is linear. Sorry, I'm writing with the mouse. So this is a linear function, okay? The same thing goes here, okay? Okay. Another way to increase linearity. So this is how to increase linearity also. So look at this. The linear portion is just this area here, right? But how to increase linearity? Well, we can increase linearity by increasing V over drive, because as you increase V over drive, you make this ratio smaller and smaller and smaller. So this makes this linearity higher and higher. So if you increase V over drive, you have a larger area, so like a larger range of linearity. So for example, if you work with this V over drive 0.2, this is, you can say that this is your linearity region, right? But if you increase to this one, you see from here, you know, you can assume that this is the line here is just linear from this point to this point, right? Now, if you increase to V over drive of 0.4, now you have the linearity up to here, right? See, the linearity now is much larger. So it's all this is linear, right? Another way also is to increase I, okay? So to increase the gain and so on, okay? So this is how to increase linearity of this. Then we started to talk about the small signal. So this was the large signal, the DC analysis, okay? Again, you need to distinguish between the DC analysis and how we treat the circuit in DC analysis and the AC analysis or the small signal operation. These are two different approaches, okay? In DC analysis, we keep the transistor, we assume the signals are large, so we don't replace the transistor with this model, we just use the KCL, KVL, you know, and these analysis techniques. In small signal operation, we do the AC analysis, and in AC analysis we said we have to do 3 things. First, we replace the transistor. We short circuit all the voltage sources. Second thing, we short circuit all the capacitors, the coupling capacitors and bypass capacitors. We don't have them here. And third thing is to replace the transistor with its model. And here we replace it with the T model. And we said that the VG1 is VCM. VCM is the common mode. So assume that the input signal here has 2 components, the large signal VCM and the small signal VID, right? But since we have differential mode, so we have half of VID here and half of VID here, okay? So this is why VG1, this voltage here, is VCM, which is the common mode, the DC input, the DC bias, plus half of the differential input. And this one has VCM minus half of the V differential, because the V differential is between this. If you subtract this minus this, okay, you end up with VID. So VID is this voltage minus this voltage. So the VCM will cancel, and you will have half VID minus half VID. This is VID. Okay, and we did the analysis this way. Okay, so this is the equivalent circuit. We replaced the transistor with the T model, and we said that, okay, GM is defined as 2ID divided by V over drive. This is from the introduction. If you go back to the introduction slide, you will find all these equations there for the MOSFET transistor. Now we know that ID, the DC current here, is half the tail current, right? So ID is half I, so it's I over 2. The 2 cancels with the 2, you end up with this value. So GM is this current, the tail current, divided by, tail current is this one here, this current here, divided by V over drive. Okay, now if you look at one leg, sometimes it's easier to analyze just one half of the differential pair because they are symmetric, right? So if you analyze one half here, so how to find V output one, the voltage here. Okay, the voltage here is this current multiplied by this resistance, right? Okay, and how much is this current? This current is GM times VGS, if you remember. The current here is GM VGS. Where's VGS? VGS is from this point to this point, right? So, and this is 1 over GM, right? So VGS is this voltage here, and this is a virtual ground, okay? Why is this virtual ground? Because you have a symmetric signal in the input for the common mode, and you remove this DC because you open circuit, you know, the DC current. And since the voltage here is going to be 0, minus VSS is going to be 0, then this is also a 0, but a virtual ground, okay? So if you assume this is a virtual ground, so this is 0. So VGS is nothing but VID over 2. Because this VID over 2 is the voltage from here to the ground. And this is a virtual ground, so VID over 2 is the same as VGS. So this current here is GM times VID over 2. Now we multiply this current by RD with a negative sign. Why negative sign? Because this is upside down. The current is going this way. So I think that we understand this. We did this many times, right? So you have to multiply by a negative sign because the current goes this way, and we're measuring the output as this is plus, right? So it's minus GM VID over 2 times RD. The same thing if you do it this side, but without a negative sign here, right? Because the current is going up this way. You can put the current down, but you have to say that it's negative, right? So negative times negative is positive. So in this side, the voltage is, the output voltage is GM VID over 2 times RD. Okay, now V output differential, which is this. So V output differential is what? V output differential, let me write it here. So V out differential is V out 2 minus V out 1. Okay. This is 2. This is 2. Okay. So V output differential, which is this one here, is this voltage minus this voltage. If you subtract them, you get GMRD. So this is the very famous and very common amplification or gain for any MOSFET transistor. The only difference is that you don't have the negative sign here, right? We don't have minus G. Why? Because you are taking the output as differentially between output 2 and output 1. Okay. Here, this is just like an extra information, and we already said that why we prefer. I think there's a mistake in the previous slides. I figured it out. Here, we don't prefer the single-ended over the differential pair. We prefer the differential pair over the single-ended. I think the original slides were written in incorrect information. So the reason why we prefer differential pairs to single-ended amplifier, these are the 2 reasons that I mentioned before. It's insensitive to the interference. Why? Because the interference is a common mode signal. The interference hits the 2 inputs at the same time. So it will be rejected, similar to the VCM. And it does not need bypass coupling capacitor. We don't need for the DC to couple with any capacitor. Any questions? Do you have any questions? Do they assume that no questions means good news or bad news? Is there anything that's not clear, or are you following with me, or?
I think it's pretty clear.
Clear? Okay. Okay, thank you. Feel free to raise your hand and ask any question at any time, okay? Okay. This slide is just repeating the same thing, all what we see, that we already said that before. How to calculate GM. GM, as I mentioned, is 2ID divided by V over drive, and since ID equals I capital D, like the DC current is half the tail current, so at the end, GM is I divided by V over drive. And if you'd like to consider here in this equation here, we didn't consider the early effect, right? The channel modulation. So these are two equivalent terms. If I say neglect channel modulation effect, or if I say neglect the early voltage effect, I mean to neglect RO, okay? But if RO is not neglected, then we have to calculate RO. And RO is the absolute value of VA divided by ID, right? And ID is I over 2, okay? And in this case, can someone tell me if I don't neglect RO here, how much is this going to be? Well, if you go back to the transistor here, since this is ground, right? So this is ground. In AC, this is ground. So RO is here, right? RO is going to be here. Okay, from the drain to the source, right? So RO, if you go back to the AC equivalent, let me delete this. Where's RO here? RO is here, from this one here, from this point here, all the way to the ground, right? And instead of drawing it here, or instead of drawing RO from here to here, from this output to the ground, we can draw it here, right? And this is RO. Do you follow this? So if you would like to consider RO, you have to connect it between the output, the drain, to the source, right? But instead of drawing it here, I will draw it here. So now you can see that RO is now parallel to RD. So if you need to consider the early effect or the channel modulation effect, then you make this RD parallel to RO. Okay. But if RO is neglected, then just RD. Okay. As I mentioned before, we can also analyze half the circuit. If you analyze half the circuit, in this case, the input here is going to be VID over 2, and the output here is going to be minus V output differential, V output D divided by 2. Okay, why minus? Because this is the polarity is this way. This is this minus this, so this has to be minus. Okay, and why V output differential over 2? Because this is V output differential, and if you consider just this half, you divide everything by 2. So this has to be V output differential by 2. So if you'd like to analyze the whole differential amplifier in a simpler way, just put a split line here and make it one circuit, one transistor, because they are symmetric, right? So if you do this, you're gonna have this one here, okay? If you have this one, then you can find the gain if you divide this by this. What's the gain of this one? This is a common source amplifier, easy one. So the gain is minus GM So this one is minus V output D over 2. So you can say that minus V output D over 2 over V input D over 2 equals minus GM RD parallel to RO, right? But since there is a minus here, you cancel this minus with the minus or the negative sign of the equation, and you end up with a positive one, okay? And you cancel the 2 with the 2, and you end up of V output D divided by V input. So analyzing half the circle give you exactly the same gain equation formula, for the gain formula as we have before, okay? So you can analyze half the circuit and get the same result. Okay, let's take this example. We have a differential pair that's supplied by VDD and this current source to bias the two transistors, and it's connected in a differential mode, like in a differential mode. And the two resistors here are identical. The two, I assume the two transistors are matched. And these are the parameters we have. We have I as 0.5 ampere. This tail current source is 0.5 amperes. And VID max is 0.25 volt. Okay. Remember the VID max? VID max is the maximum input differential input, right? And if you go back a little bit, what was the maximum differential input that we assumed? If you go back to the nonlinear curves, this is, right? So here, this is the maximum input differential, the differential input, right? We cannot increase the input, the differential input above square root of 2 times V over drive. Okay, so if we go back, so VID max is 0.25 V or volts. The transconductance parameter, process parameter of this transistor is 400 microamperes per volt square. This is Kn prime. And the differential gain is 10 volt. So the differential gain is nothing but V output D divided by V input differential. And the question is to design this circuit by finding RD and W over L. So this is a design question, okay? Well, as I mentioned before, that VID max is square root of 2 times V over drive, right? This from the early equations. So from this equation, we can find V over drive. Why do we need V over drive? Because we need to design this, we need GM, the transconductance of the transistor. So to find GM, we know that GM, as we mentioned before, is I over V over drive. So we need to find V over drive. And this piece of information gives us how to find V over drive. VID max, and again, what's the VID max? Is the input voltage, the maximum input voltage that can steer all the current from this side to this side. If you apply 0.25 volt to this differential pair, the current here will be this current, will be 0.5. If you apply this voltage here, okay? If you apply 0.25 volt here, the current in this leg will be the complete 0.5 amperes from the tail current. And again, if you apply it in the negative of it, then you will steer all the current I to this side. Okay, so from this maximum input, we can determine V over drive as 0.18. And we use V over drive to find GM. So it's 0.5 over V over drive, which is going to give you 2.8 milliampere per volt. Again, why do we need GM? Because we know that from the previous slides that the gain is nothing but GM times RD. So this is how to find RD. So RD is A differential divided by GM. Okay. Again, we should here, because we don't have any information about the channel modulation effect. So we have to assume that we neglect channel modulation or we neglect RO. So if RO is given, or any information about, like, for example, if I give you the early voltage, then you have to find RO, okay? Again, how to find RO if V early is given, you can use this equation here. If I give you V early, and I said don't neglect the early effect or don't neglect the channel modulation, you find RO by dividing the V early over I over 2. Okay. Okay, now we find RD. RD is going to be 3.6 kilo ohm, so we have to design this by 3.6 kilo ohm. How about the designing of the dimensions or the geometry of the transistors? Well, we know that, you remember this formula from introductory file or a chapter. So ID1 is the same as ID2. This is the DC component, which is half of the tail current. So it's Kn prime over 2 times W over L times V over drive squared. And V over drive is VGS minus VT, okay? So we know V over drive, we know Kn prime, and we cancel this 2 with this 2, and we know I, so we substitute the value and solve for V, for omega, for W over L. This gives us 38.6, and this is unitless because this is this is dimensionless. I mean, like it's a W with the meters and L with meters or micrometers, okay? So this is a simple question that you can solve for this. You know, like this combines the DC analysis and AC analysis together. So we can see that this is a DC analysis equation, and this is an AC analysis equation. This is a DC analysis. This is like the large signal analysis formula and so on. Okay, now normally in as I mentioned before, we try to avoid in design. Do you have any questions before we continue? Okay, so we always try in designing or fabricating ICs, we try to avoid resistances and large capacitances. So in this case, as I mentioned before, maybe in the current source chapter, we try to avoid having or building the resistors. Instead, we replace these resistors with a current source. So designing current source with a transistor is much easier and much preferable than implementing a resistor. Okay, so we can replace this resistor with a current source with a MOSFET transistor, and we also replace this with a MOSFET transistor. So this is how we do this. Okay, so to obtain higher gain, and this gives us higher gain. Why? Because these two transistors have a very large, you know, what's RD? Where's RD here? You know, if you can ask the question, this is a resistor. Where is this resistor here? It's actually RO, because any transistor has an RO. So when you put a transistor replacing a resistor, you're actually utilizing its RO as the resistor. And since RO is very large, then you increase RD. Okay, so by inserting a transistor here, you're actually increasing RD. And a question, why do we need to increase RD? Why it's preferable to increase RD? Oh, it's mentioned here. So to have a higher gain, right? Because we know that from this equation here, that the gain is proportional to RD. So the gain is GM times RD. The higher the RD, the higher the gain. So once you increase RD, then you have a higher gain. Okay, but of course to certain limits, you cannot, like someone can say, okay, why don't we have this as an infinity? No, you have to have a current here, so you have to increase this to a certain limit. Okay, so now how much is the gain of this differential amplifier? So this is a differential pair. These are the two differential, the main transistors, and these two transistors are replacing the RDs. Okay, so this is not a cascade, right? It looks like a cascade, but this is a differential pair with an active load, or a transistor replacing the loads or the RDs. Okay, we can even have a cascade here. You know, we can put two transistors here and two transistors. And if you go to the textbook, you will find this circuit. You know, you can replace this single transistor current source with a cascade current source. Okay, but it's gonna be like higher, you know, and higher. So the gain is minus GM, GM times RD. Now RD is RO3, right? RD is RO3 plus or parallel to the RO of this one as we did before. So this one has an RO1 and this is has RO, I'm sorry, this is has RO3. So the gain is GM times RO1 parallel to RO3. Okay. Again, we assume that RO3 is the same as RO4, RO1 is the same as RO2, and GM1 is the same as GM2. Okay, so this is the gain will be GM1 or 2, RO1 or 2, parallel to RO3 or 4. Okay. Any question about this slide? Okay. Now we go to the something called common mode rejection ratio. We need to, this is a parameter of like measuring how good or how perfect the differential pair in rejecting common mode signals and amplifying the differential signal together at the same time. So if we'd like to give a parameter or a measure that shows you how good the amplifier, this amplifier, in rejecting the signal, the noise, and amplifying the signal at the same time. Well, the best thing to do is to see the ratio between the differential gain and the common mode gain. And if this number is very large, then this transistor or this amplifier is capable of amplifying the good signal and rejecting the bad signal or the common mode signal. Okay, so how to do this? First of all, we will study the common mode gain, and then we see this ratio between the differential gain and the common mode gain. Okay, so in the previous slides here, we studied the differential gain, right? And now we are going to study how much is the differential, the common mode gain. Okay, so we make the circuit more realistic by adding a current source here with a resistor. Okay, so again, you can think of this as a transistor, a MOSFET transistor, and this RSS is its RO, right? So any current source could be replaced by a transistor with a parallel resistor. So it's not an ideal. Before we assumed that this is an ideal current source, now it is not. So we have a degenerated source here. So the source now is not grounded directly, but it's connected through RSS to the ground. But again, for the circuit analysis, for the AC analysis, this is not gonna change too much. Let's just go ahead and find the common mode gain. Okay, so if we'd like to put this circuit in the AC analysis, we have to connect this to the ground, connect this to the ground. So this VDD becomes ground. This minus VAS becomes ground. And this current source, since it's a DC current source, it's open circuited now. And you end up just, the RSS will remain. So this is the circuit after removing the DC sources. We don't have coupling capacitors, so we don't short circuit anything. So the next step is to replace these transistors with their T model or hybrid pi model. So this is the circuit that we need to analyze, okay, to find the common mode gain, okay. Now, before we do this, we know from the beginning that the common mode gain is 0, right? Because this configuration does not amplify common mode signal. We know this. So just we're going to prove something we already know. So how to find the input signal, okay? So the input signal here is from this point, from G, the gate, to the ground, which is this voltage here plus this voltage, right? So this voltage, and this is the current, which is GM times VGS. Remember, this current is GM times VGS. So this current I, if you assume it's I, then you multiply I by 1 over GM plus 2I. Why we multiply here 2I by RSS? Because 1I here and 1I here, you combine here and you have 2I. So 2I times RSS gives you the voltage drop here, and 1I times 1 over GM gives you the drop here. If you add these according to KVL, this voltage to this voltage gives you the V input common mode. So the V input common mode is I divided by GM, which is this voltage drop here, plus 2I times RSS, which is this voltage drop here. We rearrange this equation to solve for I. So I will be VICM divided by 1 over GM plus 2 RS. Just rearrange this equation. Now we know the current here. How much is the voltage here? V output 1. So V output 1 is the voltage across RD. So it's going to be negative because the current is going this way. So the current I is going this way. Okay. And we need to measure this voltage to the ground, right? So we have to have a minus sign, and we multiply this I by RD. Okay, this I, which is VICM over 1 over GM plus 2 RSS times RD. Okay, so this is V output 1, which is the same as V output 2. So now V output 1 is the same as V output 2, and if you simplify this, you will find that 2 RSS is dominant, so it's much bigger than 1 over GM. So you can cancel this term, and you end up with RD over 2 RSS times VICM, V input common mode. Now, if V output 1 is the same as V output 2, then the V output differential responding to this common mode signal is 0. Okay. So if V output differential is 0, then the common mode gain is also 0, because common mode gain is nothing but V output differential over V input CM, common mode. And since this is 0, then this is also the whole thing will be 0. So to make it different a little bit, we have to assume any mismatching. Okay. So if there's any mismatch between these two legs, you will have a voltage here. Okay, if these two legs are exactly matched and exactly identical, the output here will be 0 for a common mode input. I'm talking about common mode input here. If this voltage is exactly the same as this voltage, this transistor is exactly the same as this transistor, this RD is exactly the same as RD, and this RSS is common, then the two sides are exactly identical, then this voltage will be the same as this voltage, and the difference will be 0. So you have to assume some like kind of mismatch. We can how to add this mismatch? We can add the mismatch in RD. We can add the mismatch in the transistor itself. So these are the two possibilities. GM is not the same. W over L is not the same. Kn is not the same. Any parameter, or RDs are not the same. So here we will assume that RD is in one transistor or one leg is shifted or mismatched by delta R. So assume that for the first transistor we have RD, and the second one we have RD plus delta RD. So V output 1 is minus RD over 2 RSS times VICM, and for the second one V output 2 is RD plus delta RD, which is the mismatch, divided by 2 RSS times VICM. Now, if you find if you'd like to find the output differential voltage, you subtract V output 2 minus V output 1. So this gives you minus delta R D over 2 RSS times VI common mode. If delta RD is 0, then this is 0. Okay. Now, how much is A common mode? So A common mode is V output differential, which is this part here, divided by 2 RSS. Okay. So we divide, common mode is V out differential divided by VICM, which is minus delta RD. If you divide this, okay, by VICM, VICM will cancel, right? If you divide this by VICM, we divide this value here by VICM, this is V out differential, this is going to give you this one, okay? Which could be defined as this one if you'd like to find the ratio between RD and RN. So this is the original gain, right? This is the original value, okay? And you multiply it by delta RD divided by RD. Now, the measure of the powerfulness, or how powerful this amplifier is called the common mode rejection ratio. Common mode rejection ratio. So this is the common mode rejection ratio. It tells you how powerful this amplifier is to amplify the differential signal and reject the common mode signal. So it's the ratio between the differential gain over the common mode gain. Okay, so how to define the common mode rejection ratio is the ratio between the differential gain to the common mode gain. We know that this is a very large value and this is a very small value, so this ratio should be large, very large. It's in millions or hundreds of millions. It's a very large ratio. Okay, and if you go to the data sheet of 741, you can figure out how much the common mode rejection ratio. So it's the ratio between how much the differential gain is divided by the common mode gain. Okay. Any questions so far? Okay, let me quickly give you an example. Okay, so we have a MOS differential amplifier with the following parameters. So we have V over drive voltage as 0.15 volt. We have GM GM is 2 milliamperes per volt per volt, and we have Kn prime equals 500 microamperes per volt square. Okay. The question is, or the required is, to find I and W over L. Any idea how to solve this? So we are given these three piece of information. So V over drive is this, GM is this, Kn prime is this, and we need to find the tail current source I and the dimensions of the transistor. So this is differential amplifier or differential pair with these parameters. Any idea how to find I and W over L? Go back through to the slides and try to see the equations and how to utilize these equations to find these things.
You can find I using GM equals I over V over V.
That's correct. That's correct. Yes. So we know that GM is I over V over drive. So, you know, this course is all about, you know, applying these formulas. So you have the formulas, and I will give you the formulas, you know, you most likely will be given. So try to understand how to apply them, how to use them. That's it. You know, to understand the main concept, know how to use the formulas and utilize them. That's it, you know. I know it's, you know, we have many formulas, but you need to know how to utilize them, how to use them, okay? So GM, as we mentioned before, is actually, you know, originally this was TID, 2ID divided by V over drive voltage, right? And we said that we know that ID is I over 2, right? It's half the tail current. So this means this is I over V over drive. And we know that I is, we need to find I, okay? So we need to find I. So I is GM times V over drive voltage, okay? If you multiply GM by V over drive, what you get is 0.3 milliampere, of course, okay? Because this is milli and this is volt, okay? Okay, next, how to find this one?
You would use the V over drive equals square root I over K prime.
Yes, that's correct. And where did we get this formula from? We can go backward. So we get this from the formula that says ID equals half Kn prime times W over L times V over drive squared, right? This is the original formula from the introduction, from the first introduction. Okay, this is the DC current as a function of VGS, because inside here there's a VGS, right? So this is the nonlinear link between ID and the VGS. This equation here is similar to the beta IB in the bipolar junction transistor. This links the output current, DC current, to the input DC voltage, while the IC equals beta IB links the output current to the input current. Why? Because the bipolar junction transistor is a current source, current controlled current source. This transistor is a voltage controlled, because inside here, remember, this is V over drive equals VGS minus V threshold, okay? And V threshold is constant. So ID now is a function of VGS. This is the input voltage, this is the output current. Here, this is the input current and this is the output current. The bipolar junction transistor is a transistor that's controlled by its input current. The MOSFET transistor is a transistor that has the current controlled by its input voltage. So this is the original equation. Okay, now we know that ID from this one, ID equals I over 2. So this is I over 2 equals Kn prime over 2 times W over L times V over drive squared, right? Now we can cancel this 2 with this 2, and we solve for W over L. So W over L will be I divided by Kn prime divided by V over drive squared. Okay, which is the same equation as you mentioned, but the one you mentioned was for solve when you solve for V over drive. Okay, so how much is I? I is known here. We already calculated here. I. Kn prime is this one here. V over drive is given here. So if you substitute these numbers, you will get 26.7. And again, this is a ratio, so it's a dimensions. So things are simple once you know how to use or utilize these equations. So this is straightforward. Okay. And we can play with this. Like, for example, I can give you, or I can, for example, not give you GM directly, and I can give you the gain. Okay, and I can give you the gain. The gain is GM times RD, right? If you know RD and if you know the gain, you can find GM, and you can use GM to find I and so on. Okay, so like we can use the other equations to manipulate the problem. Okay. Any questions? I'd like quickly to go to the multi-stage amplifier. Well, when you build a multi-stage amplifier or a package of operation amplifier like the 741, so inside this tiny integrated circuit, there are many circuits and many stages, okay? For example, if you consider just 3 stages like this, A1, A2, A3, these are the, like if you abstract the whole 741 or the whole operation amplifier, we can abstract it into 3 stages. We assume the first stage is the differential pair. So the first stage should be this stage here, the differential pair, okay? Oops, this one here, okay? So the first stage has nothing to do with too much amplification. We don't need too much amplification from the first stage. We needed to reject common mode signal, to reduce the noise, and give a little bit of gain, but not too much, okay? And the second stage is the stage that's responsible for the gain. This is the one that gives you the gain. So maybe this one will multiply by, give you a gain of 5, 10, something like this. This one might give you, can give you a higher gain. And this is why this is a differential pair. This could be a common source, or if you're talking about the bipolar junction transistor, common emitter, because we know that the common source and common emitter are good for gain, but they are bad for input impedance or output impedance. Common collector is better, so we have to, maybe this stage also can consist of a common collector followed by a common emitter, followed by another common collector. So, the middle gain stage could be also composed of different stages. But the main goal of this stage is to have the amplification. The final gate, the final stage, it's not concerned about gain, but it's concerned about power amplifier. So this is a power amplifier. Why it's a power amplifier? Because the load most likely is going to be a small load. So it's a high load means it's a small value, like 8 ohms, 10 ohms, or something like a speaker or something. So you need to have a transistor that can deliver this high power, this high current. It's not only a voltage gain, it has to have a current gain. So this is a power amplifier. Unfortunately, we're not going to cover power amplifier in this course, but these are the main points. So the first stage is responsible for the noise rejection. Second stage gives you signal gain, and the last stage should give you a power amplifier. And here we are concerned about linearity in the power amplifier. Okay. So again, the differential, the input stage is a differential pair. Okay, and it gives you some gain here and some gain here, but the main function of the first stage is the common mode rejection. So it rejects the common mode signal. Okay, the output stage is not a differential pair. It's a single-ended output stage, and it's has a gain and power. It's a power amplifier, and it does a resistance transformation, meaning that these stages, the previous stages, will not see the low resistance here. We will see it very high on this side, because this operation amplifier has a very high input impedance. So this amplifier will not see this low impedance at the output. So this is why we call it a resistance transformation. So you transform this low resistance at the output, and will be seen by the second stage as a high resistance. Okay. And the final stage will see just the low resistance. So this one is work harshly with the load, okay? And this is why it has to be a power amplifier. So simply we can have an operational amplifier here, the differential pair here, a single-ended stage like common source or whatever, or common emitter, and at the end, a common collector power amplifier would be good to serve the output, okay? Let's study this circuit here. So this is a 2-stage CMOS op amp, okay? Here we have the differential pair and the mid or the intermediate stage. We don't have the output stage, or we can combine the intermediate stage and the output stage. Can you tell me the components roughly? And I know this looks scary a little bit, but we will analyze it and we'll find it very easy. Okay, this is example 9.6 in the textbook. Can you tell me quickly what are the main components of this circuit? Like you can say, okay, Q1, Q2 resemble has this function, Q5 has this function, Q7, Q6 works as this. Can someone try to analyze this circuit? Give me determination or information about the pieces of this circuit. Based on the information that we have studied so far. We studied single-ended transistor amplifiers. We studied differential pairs. We studied current sources. So just give me idea of components of this circuit. Like, for example, can you tell me where's the differential pair here? What are the transistors that constitute the differential pair? Anyone?
Just a guess. Q1, Q3 is they are the same with the one you just treated. Q1, Q3, Q2, Q4, and Q8 and Q7. It's like a mirror. Just guess.
Okay, actually the differential pair is these two, right? This is the differential pair. Why? Because it has the inverting input and the non-inverting input, right? So this is the differential pair. So we have a PMOS differential pair. The only thing it's upside down, you know. The previous ones, we have the tailgate on the bottom. This one, the tailgate on the top. Why? Because this is a PMOS, okay? This is PMOS and this is PMOS, right? So this is the differential pair. So Q1 and Q2 are a differential pairs. How about Q8 and Q5?
Is that a, what is it, current mirror?
Current mirror, that's correct, that's correct. We need to have a precise current here, the current, the tail current, okay? Again, this is upside down, right? The tail current on top, because this is a PMOS. If it was an NMOS as before, the tail current is here, right? Here, okay? But in our case here, the tail current is on top. Okay, so this is a current mirror. We have an excellent current source here, and we'd like to mirror it here. So I will be the same as IRF, assuming Q8 is matched with Q5. Okay, and I'd like you to go to example 9.6. I'm not going to do it here. We can discuss next time if you want, but go to the example 9.6 and understand it. You'll be able to analyze this circuit, the whole circuit, DC and AC. And this is very important. Okay, so I need you to go today after you finish and study example 9.6 in the textbook. Okay, so this is a current mirror. Once we know W over L here and W over L here, we can determine the relationship between I and RF. Good. How about this one here? Q3 and Q4. Again, this is a current mirror, right? This is another current mirror. Why? Because you have a good current here, and you'd like to replicate it in these two branches. So this is actually it's an active loaded. You know, and instead of having RS here and RS here, which resemble RD and RD in the NMOS, we designed them because we don't want to see any resistors here. So instead of having a resistor here or a resistor here to bias these transistors, we bias them using this current mirror. Okay, so it's an active loaded differential pair. Okay. Now, how about Q5, Q6? This one. This one. What's this transistor? This is a common source amplifier. You can see we apply the differential input here, and we take the output from here. So this is the output of the first stage. So this is the first stage, the differential pair. You apply the input here and you take the output. I said you can take the output from the two outputs differentially or single-ended. Here we are taking this output and we're ignoring this output. We're not taking anything from here. So this is the input of the first stage is this plus and minus. So you put a source here and you apply this to the input. Now you take the output from here. So where's the output? Our output actually is taken from here to the next stage. So this is the next stage. So this is common source amplifier. So the next stage is a common source amplifier, right? Okay, this was supposed to be RD, sorry, right? RD of this common source. But instead of RD, we used a current source that is mirrored from this current mirror. We mirror IRF to Q5, and we mirror it to actually the output of Q7 as well. So if this matches this, this current will be the same as this current, will be the same as this current. Okay, I will delete the marks so you can see it, okay? So now can you see this? So you are mirroring the current in this transistor to this transistor and this transistor. These two transistors are parallel now, right? You apply this to the gate, you apply this to the gate. So this transistor, if you have the same dimension, then it's a current mirror. So this is, if this is I7 is the same as this one, this is gonna be I as well, okay? This capacitor is called compensation. So this is not out of our scope, but this is something, you know, for compensation. We'll talk about it later on. But so see, this is why we say it's two stages. Where are these two stages? The first one is the differential pair, PMOSFET, using a current mirror as the tail current, using current active load. And instead of RS and RS, we use the transistors. And then the output of this first stage is connected to a common source stage with an active load of another current mirror from Q8 and Q7, okay? So I need you to go through example 9.6. See the analysis, very easy. The DC analysis, the AC analysis, replace the transistor with its RO. So this one has RO, this one has RO, this one has RO, everyone has RO, okay? And this one has RO, and this one has RO. Everyone has an RO. So for the AC analysis, you replace all the transistors with their ROs, and you do the AC analysis, okay? So I would like you to understand how to do DC analysis and AC analysis for such a circuit, okay? DC analysis, simply we're gonna use the equation as I mentioned before, that ID equals half Kn prime W over L times V over voltage square, over drive voltage. Okay? AC analysis, the gain always is GM times something, okay? Times the resistance here. Okay? Using just these simple two equations, you can analyze the whole circuit. Okay? So that's it for today. We are done with this. Most likely, quiz 2 will be covering most of this material for this chapter, or this chapter and the previous one, the building blocks of a integrated circuit or operation amplifier, and the differential pair and multi-stage amplifiers. Okay, so please go ahead, and I will send you shortly the problem sets. And we might have like, I'll also post the tutorial video for problem solving, solve the problem, okay? Any questions?
Exactly how are we doing the quiz?
As I told you, I will create the quiz on Canvas, so it will be online. I'm still thinking of making it open book or not. I will see. We can make it open book, but you will answer it on Canvas during the allocated time, like from 9:30 to 10:30. It's going to be 1 hour approximately. You answer it on Canvas, and then you do your work on paper, okay? And scan this paper or take a photo with the, but it has to be a clear photo with your mobile phone if you don't have a scanner at home. How many of you like have problems with these technologies? Like, I mean, scanner or internet connection or webcam, these things. All of you have these things at home or at the place you are working from?
don't have a scanner.
But can you take a photo, like scan it from your
Yes.
mobile? Okay.
Yes.
And try to use any application, good application for a good scanner, not just a vague image, or like you need to have a good scanned image. Okay. So this is it. We'll try it for quiz 2. We can make a rehearsal, like like a trial one, like a practice quiz if you want. You take it on your own time, and try it, and maybe you can open the answers for multiple trials as a mock exam or mock quiz to try if you want. I can prepare one. So basically, you answer the quiz online during the time, and of course you have to be by yourself. I might ask you to use the webcam, to make sure that everyone is standing by him or herself. You answer the questions. Most of the grades will be based on the answers you have, okay? But if there's a mistake, I'm gonna look at the scanned, worksheet that you sent, you will upload. So at the end of the exam, within 10 minutes or something, you scan or you take a photocopy of your work sheet, and then you upload. Yes, Armando.
So when you want us to like scan the work and upload it, is there like a certain time limit that you want it by? Because sometimes I do have trouble uploading files.
Yes, it has to be within 10 minutes.
Okay.
Of course,
So,
of course, has to be within time limit. I cannot
Right.
leave this for 1 day or 1 hour.
Yeah, that makes sense.
So
But
yeah, try to make sure that all these things work at home. Like you have a scanner, or you have an application that can help you scan something by your mobile phone, and so on. So you need basically a good internet connection, a scanner or an application on your phone to scan the worksheet, and the webcam if you can, because we might need the webcam just to make sure that everybody's working by himself or herself. Okay. Any other questions? Okay. Thank you so much, and let me know if you have any questions. Just post your questions on the discussion forum. And again, please go to example 9.6 and try to understand how it's analyzed, and we can discuss it in the discussion forum as well, or next time when we meet. But next time we're gonna start with the new topic, which is the active filters, okay? Thank you so much, and see you next time.
have a nice one.
Thank you.
Bye.
Bye. Okay, someone says, no, I don't have webcam. Try your best to have a webcam. It's not a difficult thing. You can have it from, or can use your mobile phone. I think. I will see. I will confirm this later on. But for now, I think it's important to have a webcam. Just focus on yourself. No need to focus on the whole environment around you. Okay. Try to find one. Thank you.